Welcome back to High Performance Computing, Advanced Scientific Computing. The topic of Lecture 5 today is parallel algorithms and data structures. So we will look a little bit more into different ideas how you can actually solve a problem in parallel. We will think about some simple algorithms, but then also go to some advanced algorithms where you go to tree-based methods. And about doing so, we also will reveal a bit more what it is about with domain decomposition and why it has so much basically relationships to the parallelization problem on the one hand, and then of course also on the basically derived data structures that you have from this that you require for the message exchanges when you do things in parallel. But before we go to the topic of this lecture, let us reveal what we had the last time. So the last time we entered the world of MPI a bit more deeper, we actually had in one of the earlier lectures about MPI already collectives, and we know it's quite powerful. But in lecture 4, we also learned that it is not always basically point-to-point communication in terms of having a send and a matching receive directly as a blocking version. So you basically just wait until you get a certain response from another processor. Here instead, the idea was that you have also non-blocking communication. So immediately when you do MPI send, you go further in your program, or if you basically have MPI receive. And with this, you have to also introduce certain, let's say, synchronization aspects we will come to also in this lecture series. Again, when we talk about barriers, when we talk about MPI wait more in detail. This was just to give you the idea that MPI is much more richer than you originally maybe thought after basically having a look in lecture 2 about it. Now, when we think about more advanced concepts, another important part of it was to really think more deeply what are all the different communicators. Communicators play a very essential role in MPI. So we have always this MPI world as communicator with all the processes basically inside that we have actually created. But we also learned then in this lecture, we can manipulate this. We can actually derive new groups from it. Like we've seen here, for instance, in the example, we said, essentially, we can here do two groups. And essentially, there are two different ones we looked at in the last time. One was a very trivial one where we said we just want to maybe split a certain group into different, subgroups doing this with the MPI split command. And then we realized one important aspect of all this, that the ranks that you have then in this MPI communicators, as soon as you have a new communicator, are about to change, right? While this was from 0 till 9 in the MPI world, the rank that essentially one or more of these processors have essentially in the other world, in this other communicator that we created out of this world, is essentially not anymore the same rank. And you see several of those here in these different subgroups have the same rank. So this is important that the rank is then valid for the different communicator. A much more powerful communicator was then the Cartesian communicator, one that is very relevant also for your assignment. We have said when we have a very, straightforward domain decomposition by having an area tiled into different pieces, let's say 3 times 4. We said there's an interesting Cartesian grid that you can overlay it and then essentially have certain different communication paradigms, which really makes it much more convenient for parallel programmers to know where to send data to different tiles, especially if we said, if for instance here, would the waves be propagating from the top to the bottom, and then maybe in an iterative fashion? We need to know what are the processor ranks that actually follow. And in order to determine what are the processor ranks that are actually I have to send something to or I have to receive from, this is something where you have the shift operations. And the shift operations became very interesting because in one way they really tell you which ranks are involved, but the other means also essentially they don't do anything. So still, of course, after we have obtained these ranks, we have to shift what's relevant. This will be today a little bit more further explored. So data structures, which we need to shift, right? So what is the information we want to put from one tile to another in perhaps one time step, and another time step, and another time step? These data structures might be very complex, might be arrays or multidimensional arrays, might be also different categories of types, maybe a char combined with integers. We have to think more clearly, and that's what we do in this lecture. What is over the wire and what options I have in the MPI space to maybe also derive my own data types that I want to send in each of these iterations. However, from a practical perspective, it was also important to understand that essentially MPI communication inherently is using really cables. We have seen the optical cables, for instance, as an example with the interconnects in the last lecture, and certain elements of topologies that matter. How essentially, basically, these cores that we're going to utilize are actually used on the lower level. We have certain elements which are very specific, like I/O nodes. There you always have to think about, okay, when I want to involve I/O, then I go to specific areas. And by this, we also understood that by doing so, we maybe have a bottleneck, seeing that many of the compute nodes that you see over here want to actually access a file service with I/O, but always have to go via certain I/O nodes and to certain switches in order to basically store files. While the data silos or the data file services and storages are large enough, and the computing capacity is quite large, usually we have learned in the last lecture, the key problem or challenge in a HPC system is the network that enables this, because essentially there we have the lots of cost factors which we have between the interconnects, which makes the HPC system indeed very costly. Now, when you look this more on a, let's say, pragmatic way, how we would now implement this as MPI developers, as parallel programmers, then we have this kind of idea that essentially we have lots of data in memory in all of these different parallel processors. And all of them, at some point in time want to dump this to disk. There are different ideas why we want to do this. So we learned that, for instance, this could be post-processing after a long, let's say, simulation of numerical weather prediction. You want to do some summary statistics on it in order to also expose what would be the numerical forecast of the weather for the next 3 days. It could be also that you train a large deep learning network, and every now and then you dump the results to disk. You want to have something we call checkpointing. So you basically have the whole AI network, the neural network, and its status of training, of learning, the weights you learn in such a network dumped to disk. The same is true for almost all simulations that you have today, that we will also reveal in the second half of our lecture series, when we dive into things like computational fluid dynamics or others in biology, computational biology, and so forth. Every now and then, of course, you are required to dump all this, what you computed, into a disk or into some form of storage. So the challenge that we have there is that immediately when you consider a high number of scales, you have certain challenges. And these could be, for instance, with a file system. You see here, admittedly, a little bit trivially explained just with 5 processors. But imagine that you have maybe 5 million processors or processes running on, let's say, 250,000 cores and so on. And they want to basically all want to now dump their status to disk. You can do this master worker and thinking of collecting all the different information, which is already maybe a problem for one of the processors to keep all of that, essentially to drive it to I/O inside the memory. It could be already a problem that the memory is not large enough. But in general, you would overcommit, let's say, one processor to write everything in one data file. Then another idea would be, of course, thinking about, okay, if that's a big problem, why not everybody does its own local file, right? And again, with 5 processes, this should be not an issue to create then 5 files in the disk to dump all this data. And here the problem again is in the file systems. Usually, as we said last time, the inode creation, if you have then lots of processors that all want to create files at the same time, more or less, inside the file system, you're also running there into lots of trouble. So that also is not really a scalable technique for I/O. The modus operandi that evolved then, as we learned the last time, is really this parallel I/O that is also beautifully implemented in MPI, as we have seen also with standardized file formats. We come back to a little bit towards the end of the lecture today. But the key idea is essentially that everybody gets a shared file pointer, so to speak, to really have different locations within one data file, one parallel file, so to speak, edited at the same time. So This means not creating many files, but having one already where certain different regions in this file are already, let's say, earmarked for different processors. And by doing so, you also can now think about that this is, of course, more than a kind of logical file, because in the deep down of the physical disks of the real I/O nodes, where the data then will be stored in the end, this might be still needs to be, striped over many different disks which are available, because the memory, the storage capacity would be maybe not enough. But so this logical file that all the different processes or threads really work in are then really a typical logical file that is then striped over really physical disks. And with this, you have quite some scalability that you achieve, an interesting approach to really deal with parallel I/O. It needs certain important file systems to support this, so you don't really have this, but we need something like Lustre or the GPFS from IBM in former times, which is now also a more other key solution in IBM, as we learn for data sciences, but the same idea of a parallel file system remains. And this is all I wanted to leave on the table for you in lecture 4. The topic of today's lecture is really parallel algorithms and data structures. So we dive a little bit deeper into a couple of parallel algorithms in order to understand really what could be an idea of parallelism. We use very simple mathematical ideas like vector addition, for instance, in using MPI with collectives, but then a bit more complex one with matrix vector multiplication. However, one idea and takeaway message is that today, many of the MPI implementations have already, let's say, interesting library sets alongside it. So if you have an application domain problem, let's say you want to have a signal, an audio signal, denoised or broken into its different frequencies, then you basically have different tools, like here, the fast Fourier transform library tools, which are already implemented, and you just, let's say, conveniently use it within essentially your application. And this will be also a theme that we then have as examples for all the different lectures which will come, let's say, in the second part of our lecture series. Today, you really work here and there with MPI, but you also use MPI-enabled libraries a lot, which already take away many of your work in terms of parallelism. With this, we have some advanced parallel and scalable algorithm examples in this context. Then the second part of this lecture today is much more about the data structures, although it's directly combined with these two parallel things. So parallel algorithms and parallel domain decompositions. So this is something which always goes together essentially. And we will actually start with the second series, the second lecture today, really revealing what that means, why it is actually interconnected so much, and what could be too little parallelism and what is maybe too large parallelism. Then we have much more smarter data structures than just maybe, let's say, a Cartesian way of doing it. We have basically an example of a tree-based structure using particle interactions and force fields. But then we come to an idea where we think when we have this data structures and we want to put it, let's say, between different halos and do a swap exchange of data every iterations or every, let's say, couple of iterations, then I need to think about data types and data structures much more when it's about variables I want to send over. So how I do this and what is actually MPI really giving me in terms of a tool set in order to make this happen? Let's say a full array of physical variables in order to better understand the heights of the wave, could be wind speeds, could be also the height of the weights, as we heard the last time, from surrounding neighbors. So the data structure always plays alongside it. We will have here small illustrated examples, and I will touch on them also when we have practical lecture 5.1 the next time. We end the lecture today basically also thinking a little bit about parallel I/O. Again, because it has also an interesting data structure alongside it called the hierarchical data format, but also we will think quickly about the NetCDF format, which is also a very much known parallel file format used as a data structure for many scientific applications. And then we end with some data science example again that you already know, the data science clustering algorithm HPDB-SCAN, but we'll look a little bit more what it means for parallel O, why we're using it, and what information is stored in that file. So let's start a little bit with the learning outcomes then. So you definitively have an overview about scalable and basically data-intensive workflows today, and workloads really coming from all of these parallel algorithms. You know really more and more about the complex aspects of parallel programming. This is clear when we talk about load imbalance. We will review again Gustafson's law here in this lecture to really understand the limits of serial programming in the end by having more and more parallelization. But by having more bigger parallel programs, then usually the serial problem is not that large in this context anymore. So these are important aspects you learn today. And with this, you have really lots of foundations covered, which you also require for your scientific domain-specific applications, because many of them from the domain decomposition of the Cartesian we discussed, load imbalance, Gustafson's law, these are all applying essentially to different scientific domain-specific applications. So by then, the idea of really using this in your own simulation becomes more clear, and hopefully will also then emerge when you do your second assignment, which is then really the simulation of an ocean, where you will then also think a little bit about the concepts we have today in practice. So when we go to selected parallel learning algorithms, let's just look back a little bit what we already learned about some abstract notions of this. We said in MPI, we want to really use it for, let's say, distributed memory, which means I need always some form of communication. And I need a problem domain that I want to essentially simulate or that I want to solve in parallel. And this could be several different things. This could be a physical model here that you have of a race car being very fast and then essentially having the wind and the turbulence around it simulated. And you do this in different cores with different parts of the applications distributed. Or as we had another application, which is also very common, let's say here, heat dissipation problem that you can transfer maybe like your heat that you have here in the ground in Reykjavik in some of the floors also outside that you already can calculate how long it takes me essentially until the snow is actually melted. So all of these are things which you can use essentially parallel algorithms for, and we will essentially have a certain some form of a recipe here I want to bring across. And this is something which is almost a little bit the same in all the different parallel algorithms. And these are the kind of three steps that we will look a little bit here essentially in this kind of recipes for these two applications. And the benefit is really that the network communication underneath is something which we not really directly experience as programmers, but for this we have parallel performance analysis and other tools we will look at later. However, the parallelization methods and the domain decomposition is something we have to think clearly about it when we do MPI. We said something about halo regions, ghost regions, and we will come back to this. So in a sense, this means that it is not completely easy to do this in parallel. That's why you have a kind of recipe here. And you start usually really by applying a good parallelization method, what we call a domain decomposition. And there are different ways also how you can parallelize. You have pipelining, you have master worker paradigms, or you have the Cartesian essentially idea of doing this. It's a more geometric interpretation. So all of these are valid domain decomposition. And then you have to manually write a kind of good MPI code, or you use here and there maybe also some libraries, but you will scale across more and more processor cores. And with this getting the whole game more complicated, of course, because then the communication can maybe have an influencing factor, as we already learned the last time in one of our lectures. So in the end, then the third is a little bit interesting and tricky when you see that whatever you do on the MPI side needs to be well integrated with the problem domain side, right? So this is now something we will come back in this lecture again to really understand that, here are the physics problems, the physical formulas then that actually play a role. And you don't want to hinder those executions or the computation at last just to do communication. And this brings us back to something we call Basically, we want to always try to maximize the computation, but minimize the communication, because essentially we have CPUs we can spare, so we have more and more of them available, or GPUs. So computing is what we want, and the communication is just a side effect, but it should fit to your application domain. Now, here's a very simple example now that we want to look at. We talk about this collective functions now already quite some time. So here's the scatter function that you already know, where you have one array maybe scattered out to many. And then we already learned about the gather function. That is essentially the other way around, where we have basically an array already at my processor here, and I get basically this filled from all the surrounding processors in my communicator. So this is something we already know, and the interesting thing is we could now leverage this when we would have a very simple parallel application example. And this explains a little bit this color encoding I have here, right? We said if you want to maybe have this vector and a typical do a vector addition here, we can see that from the mathematical perspective, we have essentially the idea that we maybe can split that up in two, which is of course a very low number here, but essentially then this is the only things which I need in order to actually calculate this fellow here. And in this sense, we can put it into different chunks. We see here that essentially what we do now here is that we want to scatter, basically, right? This interesting vector just across all the ones that I have in the MPI com world. And I do the same actually with the scatter in Y, right? So, and now you can imagine that all of these X parts, yes, X parts and Y parts are remaining now on different processors in order to do the job, right? And this is now the interesting thing, because you see inherently this is independent parallel. The Z parts could be just computed by having the different Z, X, and Y parts to be added. In other words, when you look a little bit on the source code, and I will make some demonstration on this also in practical lecture 5.1, where it becomes then more clearly. But you scatter away the big array X into different X parts, which are all represented by MPI double into COM world. So everybody gets some part of it. The same you do with essentially this fellow here with Y. And what you do then is essentially in terms of these chunks, basically just do this addition on your local parts, right? So this is of course something to locally for each of them. And in order to have the full big picture, the Z, because this is now distributed in parallel, in order to get the full picture of Z, basically we need this gather operation again. So essentially saying that the Z parts we do in each of the different processors should be gathered to one Z at the end. And this makes it then to a parallel algorithm, which is admittedly very trivial, but of course shows you the excellence of doing this now on scale, right? Of course, now here with kind of this couple of processors, this is not really a big win, but if you have a large amount of processors, this could be working, and shows you just how that would be now implemented. And also takes a little bit again already the idea of the domain decomposition. So you have essentially this domain that you require and how you decompose to get the Z. And here the mathematical operation helps us very much to derive a smart domain decomposition. Now, how that would look like if we add this a little bit more broader, if we would have, let's say here, this interesting example we already started a little bit to look into when we have a matrix vector multiplication, where we also said the color encoding is here given by the mathematical rules and formulas in order to do, let's say, a matrix vector multiplication to come to a new vector array. So that's what we do, and how we can essentially then here employ a reduce operation, which again is similar like gather, but instead of just gather it in an array, we want to do directly an operation on it, like here, a simple addition. So what we have to do for this? So we start by thinking about the domain again. And this is of course something where I say it's really very similar like the ones we have seen with the ocean, but indirectly, of course, only because it's mathematically, you know, right? So here I can now see like, okay, I have a Cartesian grid, but I don't need really a regional aspect that every neighbor is communicating with every other because of the ocean idea. Here I have my mathematical operation that guides me how to basically do this domain decomposition much more than the physical idea of having waves over the ocean. And this derives, of course, your idea here, how you essentially create this from the domain decomposition and then also for how you compute it in different parts. So essentially what we already know is we would have essentially all of these different columns, right? And then we would have it similar like the vector we have just had in different C parts. So C part that we have essentially here from the arrays. And here we have, of course, the different kind of columns that we have then to multiply only with this part of the C. We know the preparing of MPI right now, so I have here a simplified demo code. I don't repeat here what we have to do again. For most of the things, of course, we need to define here the variables. And again, we have some examples in practical lecture 5.1 where you have the full source code, but for the lecture here, that's not really required. And we see here essentially that we prepare this environment and initialize the metrics just with some values. And then we basically try to have some parallel calculations on it. You also see that we just basically initialize this here for the rank 0, initialize basically the matrix and also the vector C that we basically want to, you know, getting here multiplied. And then we do a couple of things here to do essentially a kind of synchronization in order to see that usually I would maybe load this from a very large data file, very large matrix multiplications. And when I do this, you know, basically in parallel, I would do a kind of barrier to think about this. But then also what I do now is, again, similar like I did with the vector, you can imagine I scatter now essentially these columns away to different processors, like I have in the color encoding, and basically have them then here with a scatter of C, essentially, of course, the same thing. Here, it's just a vector that I can actually scatter around with its different C parts. And here I have basically the whole columns in the different B parts. And with this, you essentially can then go and iterate over this, like we know already with all of our C part, going through the number of columns I have here in my different, let's call it B parts of the matrix, right? That I will multiply with the C part that I have received, which is basically here very trivial because in this example, we just get one. But of course, here we have different columns to go through. And then, as I said, as a new part here, we have a reduce operation that now is essentially giving us per each of these different columns that I have received here. I just want to have essentially then the addition, because you see here, while the multiplication is done in each of the individual parts, you see internally in parallel, the global sum to really compute this final vector array is really with essentially doing addition. So I can use my MPI reduce and will use essentially then the idea of summarizing this with an MPI sum to just basically have all of this directly automatically in the reduce operation formed as A0 here. So admittedly, it's getting a little bit complicated more than the maybe vector plus vector that we just had, but immediately you see it's still a relatively small idea. And here's really the key essence. Think about, we use MPI reduce because essentially all the parallel aspects that we want have to be anyway summarized and build a sum. Now, what about more complicated applications? And this is now how we dive a little bit into this as a kind of outlook also, what you can expect in the second part of the lecture and what I may say examples which are very famous. I think one of the most famous parallel algorithms these days is essentially the fast Fourier transform, which is a parallel idea of making a very speed up for the discrete Fourier transform. This is essentially used in many different applications. One application I brought you here, if you have, for instance, here a sound which is actually getting from different inputs. You have here, let's say, a C, an F, an A, and a D, and all have the different frequencies. And if you know a little bit about signal processing, of course, you can mix them and they will add up to this frequency you have above. Now, the interesting thing is that you could do here something one could call a sound frequency unmixing with the DFT, right? With the fast Fourier transform in order to derive and get the original signals back, which is quite interesting. One application scenario is also if you have, let's say, one of them would be very annoying, you can actually filter that out. Or one of them might be a background noise of a hammer or some construction, you can also filter that out and what we consider noise removal in this. So it's a very famous approach, and it would take 1 or 2 lectures just to talk about fast Fourier transforms and basically how it relates now to the discrete Fourier transform. Just to give you some numbers, because essentially discrete Fourier transform is the origin of this, where you study really periodic phenomena. But the trouble of the discrete idea is that you decompose the sequence, and then you do this with many different frequencies. So you always end up with a kind of n to the square O performance, which is something very bad. We call that quadratic performance, which is essentially very slow and will add up quickly, of course, with n. So that's why basically doing it straightforward in computing is not really is really practical. And you can see here, I give you much more information about this if you want to look into the detail. This video I found quite interesting, making a good, let's say, combination to it. But the key message to really take away is that the fast Fourier transform that we also have available in some of the libraries these days is really operating on n log n instead of, you say, having a quadratic performance. So we call this a logarithmic performance, and this is of course much more faster than it is today. And many of these basically are today really included in many different libraries, which you will basically see also every now and then when you go into the HPC field, but also when we have some of these applications in our later lecture series when we talk more deeply into the application domains. So this is just one example where you would have this. And interestingly enough, if you have then a very good library tool, you almost don't see anything anymore. You see here, lots of this is already abstracted away using a certain type of library, as you have used already in some of the include statements. And here you include just a 2D problem, some FFT library. The only thing you can specify is perhaps the world of, communicating you foresee to solve the signal processing task or whatever application you essentially want to solve. And then you have different essentially distributions of the block sizes that go alongside it. That means the MPI messages that are then sent inside and to solve this really in a parallel way are almost not really visible to you, right? So you don't really program anymore the MPI collectives or so. And this is also more and more here basically common that you have some libraries using that. So another example of how you can use parallel algorithms by really taking advantage of cutting edge technologies by using libraries which are available. And they are available in different areas of science. In computational fluid dynamics, you would use OpenFOAM. They are all basically different ones, and we will have in the second part of our lecture series much more talks about this. Now, broadcast as another example, because we didn't have that yet. Also, just to give you a personal message here, that was one of the things I actually programmed, it's almost 15 years ago, I guess, when we had computational steering of large astrophysics code. And already at that time, and now you can see why the standard is so strong. It remains the same until today with MPI broadcast, where you want to basically have some parameters distributed to all the different nodes. These parameters mean I could maybe inference during the runtime some parameters here, which would be the black hole in the stars, and you can change the position. By changing the position, you have to inform all the stars, which are basically n-body simulations representing stars. You have to inform, of course, about the location of the black hole so that all the stars can now compute essentially, again, their gravity context to the black hole. So essentially here you have an idea again that broadcast needs to be very much aligned with a domain-specific code in order to make this happen. And we did the same also for plasma physics, not only astrophysics, where we then had a laser gun at that time for also having essentially a weapon against cancer explored. But it would be too long to talk too much about it. But it carries two messages. Firstly, that essentially MPI was used already 15 years ago. You see in a very same message form in broadcast, so it's a very strong standard. And secondly, it's need to be very well integrated with domain-specific code on the other hand. And this will continue. We will talk about hybrid patterns and programming patterns like stencil methods that you a little bit see explored here, and that we already had a little bit when we think about the ocean or also the heat dissipation in order to get the heat from, my time step now. That was the interesting part here. We need, of course, essentially the time step that we basically have then at the next time step already communicated to me in order to compute this. So that's why I need message exchanges and to get informed by these different processes around me. And then I can really compute the dissipation in the room according to some, let's say, interesting formula you have here, which is essentially building a so-called isotropic lattice technique and following the stencil technique that we will also reveal more in lecture 7. The same way with using then more ideas of our ocean, and you will see in our programming assignment that will be interesting of maybe have here and there non-blocking communication. You will be required to have some ships, interactions between each other, and sometimes you maybe don't really want to do blocking, but also non-blocking communication. But this is something we will see in practical lecture 5.1. And then of course, in some real domains, you will see that also when we explore a little bit in lecture 15, then also terrestrial systems much more, or climate simulations. So for climate simulations, this is of course an interesting part because we learned that there are different domain decompositions. We will there also going much more into numerical methods, what it really means to approximate with numerics. And we will see also there different domain decomposition that you see here, how we actually can also cut, let's say, the big problem of weather predictions of the whole Earth or of regional areas into smaller pieces. And all of them have physical processes and it needs interactions. And you can nicely parallelize this. And this is something what we will show in later lectures. But here also for this lecture, think about that this has already a data structure, this parallel algorithm, which is quite a standard. So here we talk about NetCDF, that is a parallel network common data form, which is always used essentially in many of those climate simulation and earth sciences in general. You would basically have a parallel NetCDF, which works nicely together with the parallel MPI that we heard the last time. We have something which works nicely together with the parallel IO file system underneath, so that basically we really can scale by having all of these written into this logical file, which is then striped over the disks, and not something like we basically see here, that everybody, only node 0, for instance, is actually writing to this because there are different options that don't really scale if you do this. Right, we will have also then in the second part of our lecture series, other types of domain-specific applications that we require to understand how parallelization and parallel algorithms are really different. Here we talk about the Monte Carlo method, which is a quite nice idea of, let's say, using stochastic methods also in HPC that are basically not directly based on known physical laws, but rather on stochastic methods where we want to learn something about the distributions and so on. It is applied here in protein folding, what we will learn in lecture 13. And then we basically also will have the rich field of molecular dynamics, material sciences, particles, force fields, where we talk about, all the different particles and how they basically will then have different codes to really simulate over time certain molecular force fields. So going really in the world of the, let's say, smaller parts in materials, where you really understand the physical movements of the atoms, right? And the molecules which are then really forming to a bigger picture. Of course, I brought you also already an appetizer of this computational fluid dynamics, which we will also have, and finite element simulations here in a small video before we stop with the first part of the lecture. That was a very short video, but I found it still very insightful. You have seen different ideas how you do this domain decomposition. You have seen stress on these materials, what happens if there's a car crash. And of course, this is something what you also very nicely can use in computational fluid dynamics and finite element simulations that we will have also in one of our lectures in the second part of our lecture series. And this will then also include, of course, much more parallel algorithms I could convey here in the first part of this lecture. And the second part of our lecture will be then talking about some more derived ideas of forming data structures out of these different ideas of parallel algorithms.